All right, we're going to get started. We have a lot of good stuff for you. Hopefully everybody's feeling good after this very nice lunch. And we had some technical problems, so the topic of our talk is not visible on the first slide, so we're just going to move to the next one. But you guys hopefully know why you're here. So my name is Ashish Kamra. I'm a senior manager at Red Hat. I lead the AI performance team at Red Hat, and with me I have Boaz, who is part of the Red Hat Performance and Scale team, and he works on distributed workload training on Kubernetes. So the talk is multi-node fine-tuning on LLMs. So let's really look at why we fine-tune LLMs in the first place. I, again, apologize for my bad throat. Hope it's not too bad for you guys to make out what I'm saying. So basically, when you're fine-tuning a large language model, you basically start with the base LLM, and you feed it domain-specific data in order to improve its accuracy specifically on the data that you're feeding to the LLM. And the result is a new fine-tuned model, which is now more aligned with the data that you fed it. And now it can adhere to your language style and the data patterns. Now, the main challenge is this process is like training. You're feeding more data to the model, so it's very, very resource intensive. And specifically, in Kubernetes, this kind of fine-tuning would require you to support high-end GPUs or accelerators. There will be scheduling complexities because you are doing it across multiple nodes, which is the topic of our talk. And that's where projects like Q can help with all the scheduling problems. But the main topic of concern is the networking latency concerns when you are trying to do training across multiple nodes, which will be the focus of our talk. So I just wanted to give a kind of a bird's eye view of what multi-node fine-tuning infrastructure can look like in general. This is not Kubernetes specific. So you have multiple compute nodes which have the GPUs or the accelerators, which are actually doing the compute-heavy task. Then you have a backend network, which is responsible for all the training traffic, all the weights and the gradients and the optimizers that you want to pass across the various GPUs. Then you have another network. So it's better to isolate networks so that you have better network performance for front-end and storage traffic. Storage is very important because you want to feed all the compute nodes with the training data set and also for taking checkpoints. So I just wanted to give a bird's eye view of this, and the focus of this talk is the backend networking part of it, and Boaz has a lot of good results to show you in that case. So we'll go through which operators were used in this particular experiment. Specifically, we're going to focus on results of TCP versus RoCE. This is RDMA over converged Ethernet. We'll have a slide for a quick overview of what RoCE is. We'll talk about LoRA fine-tuning a little bit. And then Nickel is NVIDIA's communication libraries and some of the tuning that we did to get better performance. And we'll go through a lot of results. So don't have a lot of time, so I'm just going to quickly walk through some of the operators first. So first of all, we got to detect what hardware we are using on the node. So that's where the node feature discovery operator helps us. Then we did all these experiments using NVIDIA GPUs. So for that, to put the driver on the compute node and also all the other software components that NVIDIA wants on Kubernetes, you need the NVIDIA GPU operator. We used GPU Direct, another technology from NVIDIA, so we need the NVIDIA network operator for that. We used we're passing multiple NIC ports to our training pods. So we use the multi-NIC CNI. Boaz will go in a little bit more detail on what that multi-NIC CNI is later. And then the training operator to actually orchestrate the training job. And then a bunch of storage-related options, LVM operator, the RoCE operator for consuming self-storage, and NFS. We actually only use NFS in this experiment, and the others are mostly for reference if you want to use other storage options. So this is kind of what the setup looked like for our experiments. So we only did this on like 2 nodes. One master and one worker. Each node was fitted with 8 NVIDIA A100 GPUs, 80 gig cards each, and two Mellanox ConnectX-6 cards, each with 2 ports, each port 200 gigabits per second, and then everything connected through switch. And yeah, so we have a PyTorch-based distributed training job, and Boaz will go into more details later in the slide, what that job exactly is, what it does. And so we have basically 2 pods, one on the master worker node and other one on the worker, just the worker node. Okay, so I'm just going to skip over some of these slides because don't have a lot of time to go into the details of each of the operators that we use. But again, as I said, so we use the NFT operator to discover all the features of the node, the GPU operator to lay down all the artifacts that NVIDIA, to make NVIDIA GPUs work for AI training, the network operator for some of the RDMA features from NVIDIA, and multi-NIC CNI because we need more aggregate bandwidth to drive the training traffic. So we need to pass multiple NIC ports to our pods. And finally, the Kubeflow training operator, which is the orchestrator for running the training job. So as I said, like the main thing that we want to highlight is the backend network that is very important for driving optimal performance. So, and for that, we want to make a differentiation between using TCP as your layer 3 network versus using RoCE, which is RDMA over converged Ethernet. No, this is kind of a dense slide. Don't have time to go through all of it, but just the important thing to note here is that with the RDMA over converged Ethernet, we bypass the kernel when we are doing the data transfer over the network. So instead of copying memory from the CPU memory to the network buffers, you can directly copy memory from your application bypassing the CPU and just directly over the network. And that really helps with, in case of GPUs, because there is, while doing AI training or fine-tuning, there's a lot of inter-GPU memory data transfer and memory copy that needs to happen. So using RDMA and also GPU Direct, you could actually copy data from one GPU to another just bypassing the CPU completely in the loop. That really helps with the networking, and you will see that in some of the results that Boaz will go through the subsequent slides. All right?
You good? Okay.
Did pretty well on time.
Okay, so let's talk a little bit about the result before I go into it. The thing I want you to come out with this presentation is basically you will know how to get more out of your own system if you are running any NVIDIA training or any type of training at all. You can maximize it in a couple of ways. We'll go through that when we look at the results. Some of them we'll have to go through pretty fast because, yeah, time limitation. Okay, so the training info. You can see that I'm using the MetaLlama 3B instruct for our model. And as the data set, I took 500 samples from the open web text. Just randomly reshuffle some of the examples. The training script I'm using is the FMS HF tuning, which you can create your own, but I took something that I know that has already been working and fits what I was trying to do. And the metrics. So the metrics I'm going to present, basically the results, are going to be the SM utilization, which I wrote what it is. We basically measure the percentage of streaming microprocessors on the GPU, well, the active ones. This is how we try to determine how much of the GPU are we actually using. Another way to do that is to measure the actual GPU utilization. You will see why I take both, and the power consumption, how much VRAM are we actually consuming, and the bottom line is how long it actually takes for us to complete the training. That's the most important part. Normally, people don't actually care what you're doing or how long it takes you to do it. This is the most important part, I guess. The training parameters. We'll go through this really briefly. I'm assuming the presentation will be available later on, but I will go through what's important. Basically, we're starting with a single epoch. The batch size is length, the sequence length is 4,096, which basically means we are processing 4,096 tokens for every batch. I'm going to skip this one. Oh yeah, another thing is we're doing distributed training technique, which means we're basically sharing the information across multiple GPUs and nodes. This is how we can fit really large LLMs into relatively smaller environments. Okay, so this is a basic comparison of RDMA full training without any tuning, without anything else. And we can see we are getting 37% faster compared to TCP. Now, the GPUs in both cases basically using the same amount of VRAM consumption. So you can see we basically fill up the entire VRAM allowance that we have. Oh, relative cost is like 98%. This is the network throughput. This is the network throughput for TCP versus RoCE. I'm going to call it RoCE from now on. So we can see that RoCE has traffic fluctuations that shows off that the GPUs either don't have enough horsepower to saturate the network, or they just not being used efficiently. I was trying to use both GPUs and SM utilization, like I mentioned earlier. We wanted to ascertain the actual GPU utilization. However, I found them not the most reliable metrics. You can judge for yourself, which is why I also measuring power consumption. And well, it's an additional metric to have better understanding of the actual GPU utilization. And we can see that with the RoCE, the GPUs are using 54% of the voltage allowance, while TCP is using only 45%. So if you look at power consumption, with RoCE, the GPUs are working a bit harder. Oh yeah, so let's talk about fine-tuning. So fine-tuning is a way to be more efficient with our training. We're simply updating a small portion of the model parameters. In this example, we use this for attention set. I can't really get too deep into this. Again, time limitations. I will have all of this later on, but I wrote a little bit about each of these attention sets and what their purpose is. This is the parameters we're using. I get through them right now, but I feel like we will go through them later, right, if we have the time. Now with LoRA fine-tuning, we can see that the training is 56% faster than with RoCE on TCP. So we can see we are doing a lot better now. We have shortened our training duration, and that's because we're using LoRA now, and we're only focusing on the specific layers that we are interested in. Again, in both cases, the GPU's VRAM consumption is almost identical, depending on how you look at the statistics. But we see that we are consuming a lot less VRAM now, because we basically focusing on really specific parameters, so we don't need that much VRAM anymore, which gives us the space to do more things with that VRAM. Yeah, so in terms of networking, you can see with the LoRA throughput, it has a much less fluctuation than it had before. And the average throughput below, you can see that RoCE is working a lot faster. I kept adding those SM and GPU utilization, but this is actual, so to have all the information presented. But like I said, again, it's not the most reliable thing to it. This is kind of a known thing between us AI engineers that are looking into all this training stuff. Yeah, so TCP versus LoRA power consumption. So earlier, we used about, I don't remember how much it was, 46% Yep, and now we increased our consumption. You can see in the chart by how much. And now we're getting into the important stuff, which is fine-tuning even better so you have best performance you can get out of our setup. So I don't know if this is the NVIDIA SMI topology. Up there is the command line. You can run it and you get this table. And it basically shows you the topology in your setup. And you can see in the blue square, GPU 0 is connected to all the other GPUs via 12 lanes NVLink, which is our high-speed interface for RoCE. However, routing the data through NIC 0, which is marked in a pink square, will degrade the RoCE performance. If you can see, over there in the right square, if you go through NIC 0 and NIC 1, you will go through SYS. And if you look at system here, you will see that connection is traversing through PCI as well as the SAP internet. We kind of counter the efficiency that RoCE has to offer. We don't want to do that. What we want to do is go through as little, or to work with as the minimum component as we can in order to reduce our latency and maximize our throughput. So what we can do, we can force the system. For example, if you look at GPU 0 up to GPU 3, if we can force them to go through NIC 2 and NIC 3 and NIC 4, instead of going through NIC 0 and NIC 1, you have better performance because you are moving through less components. And this is how we do it. You can create a topology XML file, and with this topology XML file, you can define which NICs to use with specific interface. And you can set that with the NVIDIA Nickel environment variable, and with that, you can force the data path. And that will increase your performance significantly, along with other parameters we're going to look into. So these are a few other parameters that we are going to apply, well, already applied. And you can kind of go through them, but you can see it's really important to set them up. For example, the algorithm Nickel is using. Nickel, by the way, is the NVIDIA communication library, which PyTorch using as a backend to move data. I don't know if I said it or not. So you can see the default is actually 3, which is not really optimal for NVMe links that I'm using. So all these buffers will, all the settings will affect all your training and how fast it goes and how much network you are using during the training. So you can do other things with the network. Okay, so now that we switched to LoRA, now we have increased the batch size. So now we're using more VRAM, right? So now we increase the sequence length to basically 8,000 up from 4,096, because we are doing 2 batches. So we're doing more training, but we are still not fully allocated all our VRAM because we still have more space. But if we increase that to 3 batches, we'll hit OEM and we'll be out of memory and we'll just crash. So let me try and show that in a better way. Maybe it will be easier to explain it. So you can see that we started training with batch size 1 and sequence length of 4,096. We fill up 98% of the VRAM. This is what I've showed you at the beginning. Now we switch to LoRA training and we focus on the specific parameters that we care about. And we still kept the batch size at 1. So the sequence length remained the same, but we are filling only 40% of the VRAM with 4,096 tokens. Now, at the next step, we increase the batch size to 2 because we now have the VRAM capacity to do that. And basically, we are training a total of 8,192 tokens, but we are filling up 75% of the VRAM. We can't increase this to 3 because we will hit OEM, what we can do, we're not going to go through that in this presentation. It's kind of out of scope. But ideally, what you want to do is increase the batch size to 3, and then reduce the sequence length, which will fill up your entire GPU VRAM, so you will allocate your resources in a better way, and you will have more tokens being processed. Let me go back there. Okay, again, TCP, GPU, SM utilization, power consumption. Okay, so power consumption is, like I said, the metric that I've seen you're taking the most hit when we are utilizing the GPUs better. So we can see that our TCP utilization is now 63%, and RoCE went to 85%. Which basically means we're using a lot of electricity, which means the GPUs are working harder. So using less network throughput, why is that important? Because we can use something like SRV, which is an operator, a different operator. We're not using it right now, but we have the option to use SRV. And with SRV, we can create multiple virtual interfaces on top of our RoCE NIC. Those interfaces basically give you the option to attach additional pods that will have that high-speed access to that network. And so you can, even if you're not using the full bandwidth on the network, you can have other pods that can use that. And the NVIDIA operator has something that is called MIG, which allows you to share GPUs across multiple pods. So you can have a few teams working, and then you can really fully utilize your GPUs, which are the most expensive thing out there right now in terms of hardware components. So this is our final results. And you can see we further improve our training time by 40%. And this is our bottom line. So that's for TCP. We started, it took us like 2,000 seconds to train things, and then we went down to 953 with LoRA, and this is with the RoCE. Now, if you look at those numbers, it doesn't look like a lot of savings, but you have to remember that's only 500,000 samples, and normally when you do some real training, it will be hundreds of millions. So that here might translate to a few minutes, but in reality, that can be translated to a few months. Oh yeah, I have a remote now. Cool. So all the files that I use to generate all this data, it's open for everyone at this GitHub. So if you want to try it yourself, all the YAMLs, all the policies, all the scripts, all in there, you can just take it and use it and do whatever you want with it. That's it. How are we with times? 10 minutes. Very good. 10 minutes is what we need for questions. Any questions? Go ahead.
There are few companies who's providing RDMA over Ethernet. NVIDIA has InfiniBand, AWS has Elastic Fiber Adapter, EFA. So how is RoCE comparing to that at the moment?
Well, it's not about how it compares, it's about how much throughput they actually offer on that line, right? So that's InfiniBand, specifically the CX6. Each of them offer like 200 gigs, and in this specific case, I had 2, right? I was not able to fully utilize that amount of throughput because I did some small things in order to not fully utilize that network and increase the training, reduce the training duration that I had. But it's all a question of throughput and the latency. Well, it depends on the model size, but throughput and latency. So it depends on what they're offering and if it supports RoCE or remote direct RDMA, which is a bit different.
Sorry.
So basically, they do support RDMA. You can transfer like GPU without having to go through the operating system. EFA does that as well, and InfiniBand does that as well. And on a cluster of 500 nodes, your nickel bandwidth, if you run a nickel test, your nickel bandwidth would be about 275 gigabytes per second. So have you seen such numbers with RoCE?
275?
Gigabytes, not bits, bytes per second.
Yeah, gigabyte per second, 275.
Oh, in this, if I could just add, like in this experiment, we showed what we did, just 2 nodes. And, we had RDMA over Ethernet. I think the problem was we didn't really have InfiniBand-based setup, right? So as you know, like for InfiniBand, you need an InfiniBand-capable switch. The good thing with Ethernet is that you can use a standard switch and just still get the benefits of RDMA.
With the 16 GPUs that I had, which might not sound a lot, but they cost as much as my apartment to buy. With the 16 GPUs that I had, I could max out at 40 gig per second. 40 gigabyte per second, yeah. Any other questions?
Since you're using FSDP, are you sharding the model across all nodes or is the model only sharded across GPUs within a node?
No, I use full FSDP, which means I shard them all across. I couldn't do it otherwise because, it's relatively, well, not anymore. Now we have models like with hundreds of millions of parameters. This has 3 billion, and I still needed to shard them across all of them in order to get it to fit, specifically with that signal stuff. Any other questions? Great. Looks like we're done early.
Okay, thank you.
Okay, thank you.